Okay, what you just saw was me adding a socket with a priority interrupt controller right here. I then also added a Nano sitting over here, and this Arduino Nano is responsible for communication with my mouse and keyboard. And in this case, I'm using a PS2 keyboard, this one sitting right down here. And then with that, I have a mouse. It's a USB mouse, just sitting up here, old Microsoft USB mouse. But I'm treating it as a PS2 mouse, so it'll fall back into PS2 mode, and I'm going to use it as a PS2 mouse. I also have an option to plug in a PS2 connector for the mouse there, but I'm instead going with this USB type of connector because it's just easier. And essentially what happens, for example, if I hit a key on the keyboard, this Nano is going to be reading the signals of the keyboard, and it's going to realize there was a key pressed, and it's going to send an interrupt over to the interrupt controller, which will then raise it up to the processor. Processor is then going to turn around and through SPI go query this Nano and ask for the details about the key press that went with that interrupt. Or if it's a mouse move, same thing. So when I press a key or I move the mouse, this Nano is tracking that data and raising an interrupt. Processor then comes back and asks for the data, and now the processor can do something with that. So that's essentially how that is all working. And of course, I have this VIA that I've shown in a previous video that helps me do all of my SPI from the processor. So at this point, I have a couple of SPI devices, and I have one, which is this Nano to talk to this screen and go to the computer. And the other is this Nano to deal with keyboard and mouse. Part of that assembly also was I had to get some resistors in here for pull-ups. I had some diodes and other miscellaneous things that I just had to get put in. But that is all taken care of. And while I was at it, I did put in this longer ISA socket that you're seeing right down here. And that's just letting me, give me another socket, but then also access to the upper address and data bits, so I can use it as a full 32-bit type of addressing and data if I get to having a card that might take advantage of that. But I populated that for now. And then added some capacitors and just things like that on the board, miscellaneous stuff. If I jump over to my computer for a second, here's the schematic for this Nano that I have sitting up here again, so that you can kind of see what that looks like. So real quick, I got a Nano, I have my PS2, I have my keyboard connections, and that's what you're seeing here. So I've got my keyboard connection, PS2 connection for mouse, also a USB connection that will get me my mouse data if I want to use that instead. So I'm using this connector and this connector right now to get me all my data into my Nano. But then I've got the actual priority interrupt controller that I also had to hook up. So let me see if I can go find that here quick. I've got that sitting right down here. And just to talk through that real briefly, this is again, priority interrupt controller up here. I'm using an 82C59-12 for the speed, so it's one of the faster ones. And the way this works is you can connect your devices with your interrupt signals. So I have all these interrupts, 0 through 7, so 8 of them. And basically, if I remember right, you need to go from a low to a high signal. And these default, if you don't connect anything to them, to a high. But if there's a transition from low to high, it basically triggers the interrupt, if you want to think of it that way. And so these are high, and you would need to bring them low and then let it go back high to show that an interrupt happened. And I've got my keyboard on this IRQ1, so basically it's going to pull it low, and then whenever there is a key pressed, I pop it high and then back low again. And that rise is what triggers that interrupt. So if an interrupt happens, then this will turn around and raise it to the processor through this signal down here on pin 17. To actually configure this device, you need to write to it with I/O, and you have your data bus, so you've got a byte of data you can write to it. And there's this one pin that lets you choose between two registers. It's pin A0 is what it's marked. And I've got that tied to bus A2 on my computer. And being that this is a 386DX, and you're talking about a 4-byte address or a 32-bit address, you need to keep this, I think you need to keep it basically on a double byte boundary. And basically that means you cannot use A1 or A0, and maybe you can, but you're not supposed to. I think the guidance is to use this A2 is what connects to A0. And then when you do that, that means that it's basically toggling A2 from low to high will let you flip between two different registers to configure this device or read back information from this device. And the processor has to communicate with this device to get information about the interrupt. So I have that tied to bus A2, and I'll show you how I'm doing the address decoding here just momentarily. I also have to pull in my I/O write and I/O read signals, and then also a signal that does basically enables this chip. It's a chip select, and I'm bringing that really from my one of my PSOCs, my address decode PSOC. So if I jump over to that address decode PSOC for a second, previously I showed how I was doing the address decode for my VIA, and here I'm now doing address decode for my interrupt controller. And I'm setting it on address hex 10. And so that's this bit pattern of A7 down to A3. It's a 00010. So that would give me my A10. And if I toggle A2 from a 0 to a 1, that takes me to an address of not 12, but 14. And I'm not sure why that wasn't saved, but that should be a 14 at that point. And so this is essentially saying, okay, I need to make sure that these bits are 00010, and then A2 is either going to be a 0 or a 1. That gives me a hex 10 or a hex 14. And I need to be in the middle of an I/O read or write, and that will enable this interrupt controller. So that is my decode logic for now. Later I've got to expand that with my A8 and higher bits and just make sure those are zeros. But this is good enough for now, since these are the only couple of devices I'm too worried about for now. So that gets me to where I have, this signal working. I've got my A2 tied into this signal right here. And there's also this, I think this is an interrupt acknowledgement that comes from the processor itself. There's also whether or not this is a master or a slave controller. I have set as a master. I can add a second one later if I want to, but for now I just have one in there. So with that, I had to also then come in and get this nano programmed. So I have just a little bit of code, and I'm not going to go through this in detail. I've posted previous videos on my 286 about this little nano and how it's doing mouse and keyboard processing. But basically, this is the same thing. I really haven't. The only thing I added in this version is I came down into this loop down here. Let me collapse some of this because this is a lot of stuff here. But I just added a line that really quickly turns on the onboard LED on the Nano if it's in the middle of actually processing a key. And it's so fast you can barely see it, but when I do press a key, I can see a real quick little flicker on the LED. That just is a quick visual for me. But other than that, this is the same code that I've previously worked with or talked about. But essentially what it's doing is it's paying attention to the keyboard and mouse. It's raising an interrupt back to the PIC, and then it's listening on SPI so that if my processor wants to get the keyboard or mouse data, it can fetch it. Then besides that, I had to go in and do a bunch of 386 updates. And really, for the most part, the code is the same as it was in my 286. So I did a lot of copying of code over and had to tweak a couple of things. But if I walk through my code here briefly on my system that you see here, I am using, again, this address of 10 for the PIC, and then it's using, it'd be 10 and 14, but it chews up this address range if I've done my math right. My VIA previous video I mentioned I'm using from 40 to 7F, and my VGA register, which I did in the last video, is this A0 to A7. You might see this note here, and I am going to set aside, there's some 486 DLC registers, and I believe those, I'd have to go back and double check, they might be in the 20 range. And I'll just maybe put that in here, but this is this 486 DLC And you're going to probably see an upcoming video where I actually take out this 386 and put in a 486 DLC, but I think this was at 20. So for now, I'll just put that as a question mark. And I'll talk more about that in a future video. But then I get into my code as I go down through this, and I now have added in some things. So there's a BIOS data area that I initialize and really fill in so that, for example, FreeDOS can use the information and use that BIOS data area. I have a procedure that sets up all my interrupts, basically which interrupts go to or point to which addresses. I have a keyboard initialization that really just clears out or sets up a buffer for the keyboard. I am not initializing the mouse right now, but I do have a procedure that initializes the mouse. Previously, I've talked about SPI init. And then I kind of come down here, and at some point I initialize my pick. And so maybe if I take a look at this pick init real quickly, let me do a find. And it's coming up on my other screen, so let me get that over here. If I go and pull up this code, this is over in, well, actually it's in my same file, this g1.asm, but this is the code that uses those registers. So basically I need to write certain bits to one register, I need to write some other bits to another register. And if you want, you can take a gander through this, and I have previous videos that go through setting up a pick and also doing this coding. But the code that's not commented, this code and this code, those three calls are part of my initialization to get the pick set up and running the way I want it to run. So that's what that initialization procedure does. And then I enable interrupts. So, I disable interrupts first thing, and then I get through all my setup, and then at the end I go ahead and enable interrupts. In a later video, I'll turn on my VIA timer, and I'll actually try to get FreeDOS working, but I still need to get my access to a CF card working to make that happen. And then it falls through into this black hole and just sits here and spins until an interrupt happens. So that's a lot of what I've been adding here. So I've got some new files. I've got a keyboard and mouse set of code, and when I do hit a key as an example, it's going to come over to this keyboard interrupt service routine. And for now, I'm not even going to write it out to my video, my VGA. I'm just going to temporarily write it out to my serial, my debug port, so out through this to the PC so I can see it on a terminal. And that's all I care about for now. It just shows that I can access my keyboard, the interrupts are working, the processor to my Nano is fetching the keyboard data, and just validate that all works fine. Later I'll comment that out, and instead when I press keys, I won't run this part, and I'll run just the rest of this, which basically gets stuff put into a buffer. And then FreeDOS will use this buffer. So this is a buffer at a very specific location as part of that BIOS data area. So for now I am populating the BIOS data area with my keys in the buffer, but I added a temporary line that also prints out the character to my terminal output. And if I go in and look at how I've set up my registers for the pick, you can see I'm using this address 10 and address 14. And again, if you want to learn more about that, I try to provide a little bit of that in an older video about priority interrupt controllers. But that is where I'm at right now. So maybe what I'll do is I'll just pull up good old TerraTerm here, and I'm going to turn on my system. I am not capturing the VGA output right now, so that is just booting up to what it normally would boot up to. But then this is what I'm showing on the serial output. So my processor, again, is writing SPI to the Nano is writing out to my PC, and you see this screen here. But what I should be able to do is come in here and now type. Oops, if I could spell, of course. Hello. Let me try this again. Hello world. So that's what I can come in here and do, and I'm obviously not processing the enter key in this specific thing. I'm only printing the ASCII, the non-enter key, but I can now type. So this is a test. The keyboard's working nice and smooth. And so my processor right now, just as a reminder, at least for this video, you can see it here in the little terminal that came up. 24 megahertz is what I'm running clock 2 at. And that means the processor is going to be running at 12 megahertz. And in a future video, I'm hoping to show you running that 486 DLC, and that'll run a 24 megahertz processor and a 24 megahertz bus. So everything will be 24 megahertz. So that'll be pretty interesting if that works out. But this is all working. So if I hit a key, I hit the A key, again, that came over here. This Nano sensed that happened. It then raised an interrupt over to the PIC. The PIC turned around and raised that up to the processor. Processor had to communicate with the PIC and get more details about the interrupt. But then it realized, okay, this is a keyboard interrupt. Now let's go ahead and query the Nano through SPI. Let's get the information about the key data that was pressed. And then, oops, I'm pressing down on that. It looks like I'm grounding something out when I do that. Which is interesting, so I'll have to double check what's going on there. Yeah, I've got something, probably something underneath that's shorting out. Interesting. So I might have something here that either I've got solder or a wire or something underneath, but I'll come back and look at that later. And I'm going to turn off my system and turn it back on since I did that. Just to let it reinitialize and make sure I can type again and didn't break something in the process here. Okay, this is a test. Okay, so that works fine. So I'll come back and see what is not quite right. I must have a bad solder connection, or it would not surprise me if I have something underneath the board that is shorting something, just a clipping or something, but I'll look at that later. But anyways, the processor then is using SPI to talk to this Nano to get the information that was pressed on the key. And mouse movement, same thing. As the mouse is moved, that data is essentially brought to the Nano, raises the event, processor comes back and gets the mouse data. And I know that sounds like a lot, maybe for something that needs to be pretty time sensitive, but I've not had any issues with that on my 286. And this can keep up, faster than I can type. And that's just me not hitting the right key when I say I can type. I've not had any issues with my typing speed and this keeping up with everything. And so we'll continue to test that as it goes. System's running 24 megahertz clock 2, 12 megahertz CLK. All the SPI is working. I did have to tweak one thing on the clock for my VIA, and I could probably pull that up real quickly too. So I have, let's see if I've got it open already. This was my circuit doing my clocks, and so I'm generating this clock here, and that's coming straight from this 24 megahertz input. I'm not going through this divider anymore. And I can delete that. I just left it for now to make sure things work as I have it before I take this out. But previously I had my VIA running off of the same thing as clock. CLK and CLK for my VIA, I run those as separate lines. I had those the same. And I knew from previous builds that I typically had to run the VIA 180 out of that, 180 degrees. So it's kind of an inverted clock. And that's what you've got here. This is a little goofy. Obviously, a double inversion is just saying, give me what I originally had. But I wanted to give nice aliases to these nets, and it seemed like I could not put that on over here. It's just something with this tooling I couldn't figure out. So my main clock is coming out of this. It's inverted. My P clock is half the speed. It's this counter, and so my P clock is half the speed of clock. But now I have my VIA running to an inverted clock, essentially. So I know this one looks inverted, but actually that inversion gets it to where I need it to be lined up with my reset. and to this clock 2. So previously my clock 2 and that weren't quite right compared to where I wanted them. So I've got my clock 2, which is good. I invert this to get all of my timing correct, and that basically comes down to something like what you would see here. And if I zoom into this, maybe a little note about that. My understanding is that when we get into this phase 1, that my clock 2 is going up, but clock should be going down. And on the second pass through that, then it actually comes up. So I think that's what I have going on. And I need to probably look at the signals on the scope to verify, but I think that is correct the way I've got this now with clock 2 down here, the inverted version of that for my clock out, and then my uninverted version, basically this is this what I'm calling clock B. And then I also have the next slower clock. This is half the speed. This would be my P clock. So this is my full speed. This is my half speed. This is my quarter speed is how that's working. Anyways, I'm rambling a little bit, but I had to move clock via off of this signal and have it use this one that's inverted compared to that one up there. And everything's running at this full speed. So everything's keeping up on my SPI, which is good. And I think the next thing I need to do is get my IDE controller running. So this is what that card looks like coming out of my... This is out of my 286, but very simple. And I think at some point, I'll probably just put this circuitry, since there's not much there, right on this board, and then just have a couple spots where I can just click in my CF cards or this little adapter, IDE adapter. So I'll have a couple IDE controller connectors here. But that's what I need to do next. And if I can get that going, then I should be able to get FreeDOS or try to get FreeDOS up and loaded. And that would be on a 386DX, which would be great. And maybe before I get to that, I am going to probably pop in this 486 DLC. So stay tuned if you're curious to see if that works like I believe it should. I should be able to just pop it in and have that work. But I'm not sure. And we'll find out once I get it and give it a shot.